day, class. Today we're picking up right where physics meets everyday life. Look around this room. Your pen rolling off the desk, the electric fan above you, even your own legs as you walked in here. They're all showing motion in action. In this lesson, we're going to explore two big types of motion, translational and rotational, and discover exactly where they show up in the real world, from the vehicles we ride to the machines we use every single day. Before we dive in, let's set our targets for today. By the end of this lesson, you should be able to compare translational and rotational motion side by side, demonstrate the relationship between linear quantities like speed and angular quantities like spinning rate, and explain real-life applications of both types of motion. Let's break that down into three concrete goals. First, we will define translational and rotational motion in our own words. Second, we will differentiate between linear quantities and angular quantities. Third, and this is the fun part, we will identify real-world examples of both right here in our own environment. Let's do a quick 30-second refresher. You already learned that motion simply means a change in an object's position over time. Nothing moves without both a where and a when. A car driving down the road, a runner sprinting toward the finish line, an airplane taking off, a ball rolling down a ramp. All of these are motion. But here's today's twist. Not all motion looks the same. Some of it carries an object from point A to point B, and some of it just spins in place. That's exactly what we're going to unpack next. Let's start with translational motion. This is the kind of motion where an object moves from one place to another. Think of a train pulling out of a station, or you walking from the back of the classroom to the front. The key idea here is that the entire object shifts position together in the same direction. A conveyor belt carrying boxes at the mall, that's translational motion too. If you can trace a clear path from a starting point to an ending point, you are looking at translational motion. Now let's look at the counterpart, rotational motion. This happens when an object spins or turns around a fixed point called an axis, like an electric fan spinning around its center, or a Ferris wheel turning on its hub. Even our planet Earth is rotating on its axis right now, which is actually why we experience day and night. Notice that the object isn't going anywhere. It stays in place. It simply turns. So how do we tell these apart at a glance? Translational motion is straight line, point-to-point movement. Rotational motion is turning around a fixed axis. But here's an important detail. Many real-world objects show both at the same time. Take a bicycle, for example. The whole bicycle translates forward down the street, while each wheel rotates around its own axle. Hold on to that bicycle image. We're coming back to it later. To describe translational motion precisely, scientists use four linear quantities. Distance tells us how much ground was covered. Displacement is the straight line change in position from start to finish. Velocity tells us both speed and direction. And acceleration tells us how quickly that velocity is changing. Let's try one together. If an object travels 20 meters in 4 seconds, its velocity is 20 divided by 4. 5 meters per second. Simple division, but it's the foundation for everything else we calculate in motion. Rotational motion needs its own vocabulary, because how many meters doesn't really apply to something that's just spinning in place. Instead, we use angular displacement. How many degrees or radians an object has turned. Angular velocity tells us how fast it's spinning, and angular acceleration tells us how quickly that spin rate is changing. Think of an electric fan speeding up from a low setting to a high setting. Here's the cheat sheet moment. Every linear quantity has a rotational twin. Distance pairs with angular displacement. Velocity pairs with angular velocity. Acceleration pairs with angular acceleration. If you remember this pairing, you will never confuse the two. The underlying concept stays the same, and only the type of motion changes. Now that we can define and describe both types of motion, let's connect the dots. In the real world, motion is rarely purely translational or purely rotational. Most machines, vehicles, and even our own bodies blend both types together. Keep that in mind as we walk through where this shows up in daily life. Let's get concrete. Think about riding in a car or pedaling a bicycle. The vehicle itself is translating, moving you from home to school. But look closely at the wheels. They are rotating the entire time, and it's actually that rotation, gripping the road, that produces the forward translation. Transportation is a perfect real-world blend of both motions working together. Even your own body demonstrates both types of motion at once. When you walk or run, you're translating across the room, but your arms and legs are rotating around your joints to make that possible. A gymnast performing a spin or a dancer completing a pirouette is showing rotational motion very clearly, often while also traveling across the floor. Motion isn't just something machines do, it's something you do every single step. Engineering takes these same principles and puts them to work at scale. Gears transmit rotational motion from one part of a machine to another. Turbines spin to generate electricity. Robotic arms in factories combine rotation at their joints with translation of the tool at the end. Even the conveyor belt moving products down an assembly line depends on rotating rollers to create smooth, forward translation. You don't need a laboratory to find rotational motion. Your own home is full of it. An electric fan spins to cool the room. A blender's blades rotate to mix your favorite smoothie. A washing machine's spin cycle uses rotation to remove water from your clothes. A doorknob turns on an axis, and the hands of an analog clock rotate around its center. Once you start noticing it, rotational motion is honestly hard to miss. Let's zoom all the way out, to planetary scale. Earth rotates on its axis once every 24 hours, which is what gives us day and night. At the very same time, Earth is translating along its orbital path around the Sun, a journey that takes a full year to complete. So the same two motions we've been discussing all class, spinning and traveling, are literally happening beneath your feet, right now, as we speak. Let's bring it all together with one story. Maria hops on her bicycle and rides to school. As she pedals, her whole body and the bike frame are translating, moving from her house to the school gate. But that only happens because her legs are rotating the pedals, which rotate the gears, which rotate the wheels. One ride, two motions, working together the entire time. This is translational and rotational motion in perfect partnership. Time to put this into practice. I want you to look at each of these 6 objects: a moving car, a ceiling fan, an elevator, a bicycle wheel, a sliding door, and a spinning top, and decide with your seatmate whether each one is translational, rotational, or both. Take about 2 minutes to discuss, and then we'll go through the answers together. Let's do a quick check before we wrap up. Number 1. What kind of motion is a spinning electric fan? Rotational? Great. Number 2. What about a moving bicycle? It's both translational and rotational together, just like Maria's ride. Number 3. Angular velocity describes what kind of motion? Rotational motion. Exactly right. Let's recap what we covered today. Translational motion is movement from one place to another. Rotational motion is spinning around a fixed axis. Linear quantities describe straight-line motion, while angular quantities describe spinning motion, and these two sets of quantities are essentially mirror images of each other. Most importantly, we saw that these motions aren't just textbook ideas. They're happening in the cars we ride, the sports we play, the machines engineers build, and even in the planet beneath our feet. That wraps up our lesson on translational and rotational motion. Before we go, take a second and look around the room. I guarantee you can now spot at least 3 examples of each motion type without even trying. Any questions before we close? Next time, we'll build on this by looking at the forces that actually cause motion to happen in the first place. Thank you, and see you in our next class.